So I'm Katie. I am the genetic counselor at the Children's Colorado group. So my goal today is to just kind of give a brief genetics 101. Is the microphone working okay?
Speak up.
Okay, I'm just getting the echo.
Yes, you are.
Yes. So I'm just going to give kind of a brief genetics 101 to help decode the language that we see in these genetic reports. I think sometimes people get reports back and there's a lot of letters and numbers and all these big words that you may not have encountered before. So it really can seem like a foreign language. So just to start from the basics really quickly, we all have trillions of cells in our bodies. They're all made up of chromosomes, which are packages of DNA. And our genes, like SYNGAP1, are segments of DNA that code for protein. And then that protein is a compound in the body that can have many different jobs. As we know, Syngap itself is very important in the brain. It's important with learning and memory. But proteins can have all sorts of different jobs within the body. So a gene is any segment of DNA that codes for a protein. We have 2 copies of most of those genes, including Syngap, and those are called alleles. So when you see in a report heterozygous, that means that there's one allele with a mutation and one without. Again, protein can have a lot of different roles in the body, and proteins are made up of smaller units called amino acids. So you'll see those on a report as different single letter codes. So I often use the analogy of a recipe, ingredients, and then the final product. So a genetic variant is any alteration in the DNA sequence that's different from what we see in the majority of people. So the variants are not automatically bad. They don't all cause problems. We all have tons of genetic variants. Many of those are benign or even advantageous in some cases. But when we're talking about genetic disease, we're typically talking about pathogenic variants. So variants that cause a disease, that cause that protein product to not work correctly. So we often refer to those types of variants as mutations. So this is kind of a schematic of what the SYNGAP1 gene looks like. It's made up of 19 different exons, and exons are sort of units within that gene. We often describe them as trains or cars on a train. And when the body reads that DNA code to make that final protein product, it's taking all the in-between information, cutting out the exons, and putting them back together to make that protein. Syngap has multiple versions of the protein that it makes, so we call these isoforms. And there is one isoform that is prominently expressed in humans that does not include exons 1 to 4. So I think this is something that a few physicians touched on yesterday. There are some hypotheses that the presentation in patients who have changes within those first 4 exons might be a little bit more mild because those exons are not being utilized in every version of the protein. So just to kind of walk through what some of these mutations can look like. Our DNA is in kind of letters, sets of 3 letters. So our body can only read that code 3 letters at a time. So anytime there's any change to that 3-letter reading frame, we can see problems. And that's one of the mechanisms that's very common within Syngap. So if you think about a very basic sentence, the cat ate the rat, a missense mutation would be a mutation in which one letter in the DNA code is changed to a different letter. So we could end up instead with the cat ate the bat. So for some missense mutations, that sentence still makes sense to some extent. There are some missense mutations that are less impactful than others. So we can also see cases where that change is more impactful. It's making a sentence that doesn't make quite as much sense anymore. So for missense changes, it's kind of on a case-by-case basis what type of impact it has on the final protein. I have to say, I'm from Colorado, so I usually use a Subaru here, but we've been taking a lot of Waymos the past couple of days, so I had to throw that in there. We can also see something called a nonsense mutation. This is where there's still a letter that's changed, but instead of introducing a different, a different Lego block in the Lego set, if you will, you're introducing what's called a stop codon. So a stop codon is a normal occurrence in the body where it's at the end of the gene and it tells the body, we're all done making this protein. If it's introduced earlier on, though, it stops that protein short. So that sentence ends early, you don't know exactly what was supposed to be said. So you might see this in a genetic report as an asterisk or an X, or you might see the letters TER for termination. We can also see changes within the DNA where there are insertions or deletions or duplications that impact that sentence in various ways. But you can see here, this is an example where there is another 3-letter word added. So you're not throwing off the way that the DNA is read 3 letters at a time. You're just adding a different word. So it does change the impact, it changes the sentence, but it is still something understandable. So if you think about a gene, this is a case where the gene would continue on, it would add this one different amino acid, but then it would continue on as normal. So you can see this also with deletions or duplications that are, again, within that 3-letter at a time reading frame. So there's a change introduced, but then sometimes it goes on and continues building the protein as normal. The place that we run into more issues, and this is a very common mutation type in Syngap, is where there is what's called a frame shift. So anytime there is an insertion, a deletion, a duplication, anything that throws off that reading frame, we have what's called a frame shift mutation. So most of the time, what happens is there is a sequence of amino acids that's added incorrectly, and then eventually the body comes upon a code for a stop codon. So again, you see that asterisk, you might see an X, but that's telling you that the protein is stopping short and it's not being coded any further. One of the things that you might also see on your child's report is this FS, an asterisk, and then a number. And what that's saying is that there is a frame shift, FS, and then 12 amino acids later, those are the building blocks of the protein, it stops short. So it's just kind of giving this letter and number code to explain exactly what's going on with that change. So this is just kind of an example test report to walk through really quickly. You guys are all very familiar with the name of the gene that we're talking about today. You'll also see, again, those letters and numbers that are explaining exactly where the change is in the DNA code. The C stands for coding, and then the change that results in the protein. So the P stands for protein. So all of that kind of alphabet soup that we often call it is actually just explaining sort of the address of where that change lives within the gene and within the protein. So why is all this important in the context of the conversation we're having today? Sometimes the specific variant that you have or the type of variant can impact what therapies might be amenable to altering or fixing that genetic mutation. So there are things like ASOs that can target specific types of genetic variants. We have something called read-through for nonsense mutations in some conditions. So it's not something that immediately is relevant right now, since we're still working out what therapies might work for Syngap. But when we get to the point that there is a trial or a therapy available, it will be helpful to understand exactly what kind of genetic mutation your child has, because it helps to understand what they might qualify for. So I tried to keep that short and sweet, but please feel free to come and find me afterwards, or reach out via email, or come see us in the clinic in Colorado. So I'm happy to chat with anybody about specific reports, specific questions about your child's testing.